On our previous video, we determined what the gravitational potential energy of the satellite when it is at rest on Earth's surface, and we determined this value to be equal to negative 3.13 times 10 to the power of 10 joules. This here is what is required for our rockets to move our satellite from this particular location, and this geosynchronous orbit, remember, has the same period as that of Earth rotating around its axis. And now, once our end goal is to place this satellite at this location, geosynchronous orbit, in this video we need to determine what the total energy is for the satellite where it is placed at this region right here. And so the total energy that we are going to determine is going to be a combination of two things. One is to not only consider kinetic energy of the satellite where it is positioned on the geosynchronous orbit, but also we need to consider what the gravitational potential energy is where it is at that particular orbit relative to the central mass, which is in this case Earth. Now, there are a couple of things to remember. From our previous video, we determined what the radius of our orbit is, and the radius of our orbit is determined to be this particular value. And to determine this, we use a third law that is connected to Kepler's, and this was instrumental in terms of using our universal gravitational constant, and finally using the mass of our central body to arrive at our distance from the center of the central body to the geosynchronous orbit based on this period. Now, this number will come handy as we move into this particular stage of our energy total where our satellite is positioned. And first is to look at what the gravitational potential is when our object, which is the satellite, is positioned at the geosynchronous orbit. This value here is represented as the formula, which we consider to be negative g multiplied by big M, which is the mass of Earth, multiplied by the mass of our satellite divided by our radius of the orbit. And this is what we're going to use for this particular formula. Now, the next one here is looking at what is the kinetic energy, which is represented as EK. And the kinetic energy is really instrumental in terms of the motion of our satellite where it is at that particular orbit part. And this value equal to EK equals half mv squared, where v is the speed of our satellite and m is the mass of the satellite. Take note here that at orbit we know that yes, the net force of our system, which is going to be in that particular location, is indeed equal to the universal gravitational law. And looking at this, we need to remember that yes, the net force is not just ma, but rather is a combination or understanding of the centripetal acceleration. And this here for our net force shows that yes, our centripetal force is at play, and our centripetal force contains the acceleration centripetally, and this is shown as yes, MAC. And we know that MAC is the same thing as M, where AC is centripetal acceleration, is equal to V squared over R. And so once we're able to understand this particular segment, we can then make this equivalence to our universal gravitational law. And this highlights that yes, the universal gravitational constant multiplied by the mass of our central body, in this case is Earth, multiplied by the mass of our satellite divided by r radius squared. Now take note that in this case we need to cancel out a couple of things. To cancel a couple of things means that yes, not only are we eliminating our radius, but also one of it, but also the mass, and therefore we have our equation to be shown in terms of v squared. But remember that instead of we removing the m, we need to express mv squared in terms of something familiar. Comes from this particular equation right over here, where we have ek to be equal to mv squared over 2. We have our particular left side to be similar to that of a part of the kinetic energy, which is shown right here and also gotten from right here. Therefore, all we have to do is rearrange this particular equation, and by so doing we'll be able to express our kinetic energy not only in terms of the universal gravitational constant, but also the mass of Earth, which is the central body, and also that of the mass of the satellite. Therefore, by rearrangement, our ek is now equal to g multiplied by our mass of our central body, which is Earth, multiplied by m, all divided by 2 times our radius of the orbit. Now remember that since we have this achieved, we are then going to introduce this into our equation for E total. We know that this value for E kinetic energy is expressed as this, which we're going to put right here, and take note that this is plus, but we have a negative for our potential energy of our satellite at that particular orbit location. Remember here that this E total can be rearranged in a way that we are going to collect our like terms, and what the result is that the combination of these indeed gives us this particular result, which is negative half multiplied by our g big M from Earth multiplied by our satellite mass divided by our radius. This here is also similar to a formula that we talked about except for the half, and this formula is exactly like this right here. And so this here is equal to eg, and therefore our E total is also expressed as the result half eg. And so these are the things to keep in mind in terms of how our E total connects to not only the kinetic energy but also the potential energy. And this is the formula that we're going to use to determine what the total energy is for an object at a specific orbital path. And so by putting our givens in the question, which is in this case we're given the following: we have our big G to be equal to 6.67 times 10 to the power of negative 11. Remember that although it might not be given directly, but you should recognize that yes, this should be researched and used. The other one here is the mass of our central body, which is Earth, to be 5.98 times 10 to the power of 24 kilograms. Also, we are given the mass of our satellite, which is equal to 5.0 times 10 to the power of 2 kilograms. And finally, we determined the radius of our orbit, which we performed on our previous video, to be equal to 4.22 times 10 to the power of 7 meters. This is obtained using our Kepler's third law, and so this is something to keep in mind when it comes to obtaining that additional variable. And so by putting these variables and their values in this particular equation, we'll be able to determine our value for the E total to be equal to negative 2.36 times 10 to the power of 9 joules. and this here is the total energy of our satellite when it is at the geosynchronous orbit. Now this value of course is a negative value, and once it is negative it means that hey, there will be some interesting things that will be considered when it comes to the work done, that is in comparison to not only the E total which we have determined now, also the E total when the object is actually at rest on Earth's surface. And this difference in energies will enable us to determine that yes, the work done that the rocket performs in moving our satellite to this location from at rest is going to be unfortunately not what we hoped to be in terms of whether it's going to make it or not. And so by so doing, what we realize is that hey, our next video we're going to analyze that particular part and also determine whether there is any form of energy that is required to make it to the escape of the potential well of planet Earth, or maybe it actually survives the trip with that much energy that is available. All the same, I hope you found this really informative. Please hit a comment down below, let me hear your thoughts about this, but that way I can talk to you soon. Stay smart as always and believe in yourselves.